You know the feeling. It's Friday afternoon, you push what you think is a simple fix, and then a few minutes later, this pops up. Deployment failed. The error message makes no sense and the pressure is on. But the most frustrating part, of course, it worked perfectly on your local machine. Right? This is the question that just haunts developers. We tend to treat our CI/CD systems, especially GitHub Actions, like this big black box. We throw some YAML at it, we push our code, and we just cross our fingers and hope for the best. We think of it as a simple automation tool. But do we ever really stop and ask what's actually happening under the hood when our code leaves our laptop? Okay, so today we are going to pull back that curtain. Our goal is to trace exactly what happens from the very moment you type git push all the way to your code going live. By the end of this, you're going to have a really clear, robust mental model of GitHub Actions, not as some YAML-y tool, but as a complete system. And that's what's going to let you build reliable production-grade pipelines that you can actually trust.
So where does it all begin? Well, everything in GitHub Actions kicks off with an event. You can think of this as the trigger, like the starting pistol for the entire race. And an event isn't just a git push. It could be someone opening a new pull request, or posting a comment on an issue, or even just a scheduled time, like a cron job. This is the signal that tells GitHub, hey, something important just happened in this repo, and you need to do something about it.
Now, that event doesn't just run random commands. It kicks off a specific workflow. The workflow is the blueprint, right? It's the master plan you've laid out in that YAML file. It's the logic that says, okay, when this specific event happens, here is the entire automated process I want you to execute. It's the high-level playbook for everything that's about to happen.
And this is the first and maybe the most fundamental question we have to answer to really get what's going on. It's obviously not running on your computer anymore, and it's not running on some server that's just sitting in the cloud waiting around. The reality is way more dynamic, and understanding it is the key to solving, I'd say, half the problems you'll ever run into. So, for real, where does the code actually run?
The answer is a runner. And the most important word here is ephemeral. A runner is a brand new, completely sterile virtual machine that GitHub spins up just for your job. And the second that job is done, it's destroyed. Think of it like a fully automated, disposable factory. When your workflow starts, GitHub instantly builds a clean, empty factory floor just to run your commands. Then it bulldozes the whole thing. And why? It's all about consistency. By starting fresh every single time, you eliminate any risk of leftover files or weird configurations from a previous run causing chaos. It is a clean slate every single time. So a pretty standard workflow might have a couple of jobs, right? You might have a build job that compiles your code and runs all the tests, and then a deploy job to push the final result to a server. On the surface, this looks totally logical. You build it, then you deploy it. Simple as that. And this is where so many of us hit a brick wall. Your build job runs perfectly. It compiles the code, the tests pass, and it creates a final package, let's call it app.zip. Then the deploy job starts and immediately fails, screaming file not found. But you just saw the build logs. The file was definitely created. So what is going on? Okay, here's what's happening. And this is the crucial insight. Each job runs in its own completely isolated disposable factory. The build job spins up on a brand new runner, it creates app.zip on its file system, and when it finishes, that entire virtual machine, the runner, the files, app.zip, everything is completely demolished. A second later, a second brand new, totally empty runner is spun up for the deploy job. Of course it can't find the file. It's looking for it in an empty factory that has zero memory of the one that just got bulldozed. The solution then is to explicitly pass the results between these isolated environments. You have to tell the build job to package up its results and upload them as an artifact to a kind of shared storage space. Then, the very first thing your deploy job has to do is explicitly download that artifact. This is the conveyor belt that connects your separate disposable factories. And honestly, understanding this one single concept, the ephemeral, isolated nature of job runners, is the key to unlocking how GitHub Actions really works. In fact, at this point, you already understand the core execution system better than most developers out there. If this model is clicking for you, consider liking the video so I know we're on the right track. Okay, so we get the model of isolated, disposable factories. Now let's scale this up to what we see in real-world production systems. The default runners that GitHub gives us are fantastic general-purpose machines. But what happens when you have more specialized needs? Maybe you're doing machine learning and you need a really powerful GPU.
Or maybe your deployment needs to connect to a database that's buried deep inside your company's private network. This brings us to a really critical decision point for any team building a serious CI/CD pipeline. Do you use the runners GitHub provides, or do you bring your own? With GitHub hosted runners, you get incredible convenience. GitHub handles the operating system, the security patches, all the maintenance, you just run your jobs. But if you need more control, like that special GPU or access to a private database, you're going to need self-hosted runners. Here, you provide the infrastructure and you have absolute control. But that control comes with responsibility. You own the maintenance, the security, and the cost of that machine.
Here's another classic production problem. Remember how every runner is a fresh, clean machine? Well, that means that every single time your workflow runs, it has to download all of your project's dependencies from scratch. Your node modules, your Python packages, all of it. This can add minutes of just pure waiting to every single run, which is not only slow, but it can get expensive. So how do we fix this? The answer is caching. If our runners are disposable factories that get torn down after time, then caching is like building a small, permanent warehouse right next to them. It lets you store files from a successful run, like all those downloaded dependencies, so that future jobs can grab them almost instantly instead of having to fetch them over the internet all over again.
And the way this works is actually really clever. When you set up caching, you give it a key that's based on your dependency lock file, like your package lock.json. What this tells GitHub is, hey, if my list of dependencies hasn't changed, then the cache is still good. Just restore it. But the moment you update a dependency, that lock file changes. The key becomes invalid, and GitHub knows it needs to fetch the new stuff and create a fresh cache. It's a simple idea, but it's an incredibly powerful way to speed up your workflows.
Now that we've got performance sorted, let's talk about making our workflows safe and reliable enough for production. First and foremost, you should never, ever put credentials like API keys or passwords directly in your YAML file. Instead, you use GitHub secrets. These are encrypted environment variables that are only exposed to the runner when it's actually running your job.
Next up, we can add another layer of protection by using environments. You can define a production environment right in GitHub and attach rules to it. For example, you can require a manual approval from a specific person or a team before any job targeting that environment is even allowed to run. This acts as a crucial safety gate, preventing accidental or unauthorized deployments to your most critical systems. It's the difference between a fully automated pipeline and a reckless one.
And this is a practice that every production pipeline should adopt, no exceptions. When you use a third-party action, don't pin it to a tag like @v4. That tag is mutable, meaning the owner can move it to point to a totally different version of the code, maybe introducing a bug or even something malicious. Instead, you should always pin the action to the full immutable commit SHA. This guarantees you are always running the exact same code every single time. It's a simple change that protects you from a whole class of supply chain attacks. Of course, even with the best design, things are still going to break. And when they do, don't just guess and push hoping for a fix. You have a really powerful debugging playbook. You can start by digging into the logs, then turn on step-level debugging for way more detail, and for those really tough problems, you can even get an interactive SSH session directly into the live runner. This lets you poke around the file system, check environment variables, and figure out exactly what's going wrong, just like you were on your own machine. So let's bring this all together. We started this journey seeing GitHub Actions as just a way to automate some commands with YAML, but now we can see it for what it truly is: a powerful, distributed system for orchestrating on-demand, isolated, and ephemeral compute environments. Every single piece we've talked about, events, jobs, runners, artifacts, caching, secrets, they're all just components of this larger system. This shift in perspective is everything. When you start thinking in terms of the system, of isolated runners, of state being passed with artifacts, of performance caching, you start designing workflows that are resilient by default. You stop fighting the tool and you start architecting with it. And asking the right question is the first step to building a CI/CD pipeline you can actually rely on. If this explainer helped you build that mental model, make sure to subscribe for more deep dives into the systems that power modern software development. Let's keep building better systems together.